Morning, everyone. This is the project 2, and we're doing a RC flight black box. I'm Eddie Shea.
I'm Alexander Trevino.
So the flight recorder has been applied to in various field of industry, including the aircraft or spacecraft, and it allows the users to see the order angles after we pull out the data from the data recorder. So what we're doing here is we're designing a small scale flight recorder for the RC aircraft to record the data and also allow the user to visualize all the data and then do analysis on their trajectory or design their flight control panels. So our project would be a flight recorder or like a flight black box specific to RC model that's in smaller scales. And our system requirements would be the system shall be able to record the Euler angle of a vehicle during flight. So it will be recording roll, pitch, yaw, and the system shall be able to detect height from the ground. So then the user can know how far is their aircraft is flying from the ground. And also the system shall be able to have a data storage system, which is essential because we want to know the roll, pitch, and yaw angles after the flight operation. So here we're using an SD card to record everything during the flight.
Now coming up to our system as a whole, as you can see, our system contains an ultrasonic sensor, a gyroscope, which is the MPU 6050 module, a micro SD card adapter with a micro SD card integrated into it, the piezo speaker, which in our case is a buzzer. It will be attached to an external power supply in order to accommodate just having a black box in a flight, the RC flight aircraft, and the Arduino Uno board itself. Libraries used were the libraries for the gyro sensor and libraries for the micro SD card adapter, which these libraries helped us integrate the pins that were used for our system, and then just how to collect data from the sensors itself. Next, we have the schematic. We can start from the top and work our way clockwise. We have the micro SD card adapter, which is plugged into the digital pins 10 through 13. We have the piezo buzzer, which is attached to digital pin 4. And digital pin 2 and 3 are attached to the echo and trig pins for the hypersonic sensor. And lastly, we have the gyroscope MPU 6050 module attached to the analog pins 4 and 5.
So going to our overall flowchart for our code, when we start the program, the Arduino will be calibrating the ultrasonic sensor based on the temperature read from the gyro sensor. It has a built-in temperature sensor. And then we'll initialize our SD card reader, and then we'll then create a blank text file in order for Arduino to write data into that file. And then our buzzer will be beeping once to tell the user that we're starting to record all the data. And then in the void loop, we have the Arduino writing all the order angles gathered from the sensor and the heights from the ultrasonic sensor, and it's written in the time domain. So when it like writing to the SD card, it will show us the real-time data. And after a specified time that we said is reached, the Arduino will be closing the text file and it will be stopped writing, and then the buzzer will be beeping again. So now the user know the record is done, and then we'll end our program.
How the ultrasonic sensor works is that it has the trigger pin that signals out a ultrasonic signal. The signal is reflected and received in the echo pin, and from there it is just just a simple calculation in order to find our distance from the outputted signal. And it is necessary for us to calibrate the system or the sensor by taking in the temperature for a certain amount of time and correcting the speed of sound.
Moving on our gyro sensor, it is a chip integrated with our Arduino. And how it works is that there's 4 membranes inside the chip. And when we roll or pitch or yaw that sensor, the membrane inside the chip will be rotating. And based on the amount of rotate, it can output a amount of current or like the amount of resistance so that the chip could tell the Arduino what's the roll, pitch, and yaw angle at the current state. And the data is collected and it will be converted to Euler angles of pitch, roll, and yaw. So moving to our micro SD card adapter, it is set up as shown in the top right of the slide. So you can see it's a pretty simple chip that has 5 pins, 6 pins, and then we'll be inserting our micro SD card to that adapter. And during the operation, our Arduino will be writing those data to the card in the following format, which we have time and pitch, roll, yaw, altitude, and temperature. And though the format, we set it up using the code that we provide to our Arduino. So that's how we make sure everything is lined up pretty good, and then it's in a well-organized format. And just for your information, our data acquisition rate is in 100 data rhythm per second, so which is fairly not too slow, but it's not like it's acceptable data rate, data collection rate at this for this project.
So now the component of the piezo buzzer module. This is a simple buzzer. This the way we used it in our system is that the buzzer sounds off in order to signal to the user that the program is running and collecting data. The system will collect data for a certain amount of time, and then once the program is done collecting data, the buzzer will signal to the user again. For this, we ended up using signaling to the buzzer to output a 7,000 hertz in order to have a good enough sound that the user can actually hear, even during a lot of noise in the environment. And our calibration method for our sonic sensor, we actually calibrated it using a certain 30 temperature samples. The way it calibrates for the distance is that it takes the 30 temperature samples, takes the average, uses the average in order to calculate or correct the speed of sound. And from the speed of sound, the corrected speed of sound, we are able to calculate the distance. And this, by calibrating the temperature in order to correct the speed of sound, this is applicable to when the temperature changes, especially for any aircraft that climbs or a car driving either from day or night.
So now we're gonna demonstrate how our system's gonna work at the smaller scale. So as you can see, when our system trying to climb, the pitch angle increases, and then when it tries to dive down, the pitch angle decreases again, and the corresponding roll angle and yaw angle is lining up with my hand's motion. So it's pretty much reliable in this scale of testing, and it also showed that our ultrasonic sensor is working in this distance range. So upon this project, we will be able to apply a more more high-end ultrasonic sensor if we're flying higher, or we can apply a common filter to our angles or our heights to filter out the noises from the environment to get a more consistent data. But one thing to notice that if we use a filter, that might be decreasing the pilot's reaction time when it sees the data or when it feels the angle or the heights. So it's something that we can do better in the future. But at this scope of the project, we are like sticking with those algorithm, and it's predicting a pretty reliable data at this time. So,
And so this is just how we distributed the workload. I implemented all the components of the programs into just one script so the whole system can work. And I also constructed the schematic for the system. Eddie formatted the slides and actually did research on the equations.
and that's all for our project. Thank you for your patience.